Hello and welcome to our panel discussion today on materials characterization. What systems do we need for tomorrow's challenges? Harsh environment electronics and high voltage in automotive, increasing miniaturization, they're all challenges that demand cleaner signals and boards. Here to discuss this we have an eminent panel. To my extreme right we have Naisbitt from Gen 3. Next to him we have Mark McMeen from Magnalytix. And sitting next to me on my right is Mike Bixenman from KYZEN Corporation and Magnalytix. Okay, so welcome, gentlemen. Let's get straight in with you, Graham. Factory automation is pushing the demands for faster results and traceable and actionable data. So, what data choices should the manufacturers be considering today?
Well, the fundamental change that has come about since October of last year is the removal of a magic number that companies have been using for at least 25 years. And it's not a one-size-fits-all. The requirement through IPC J Standard 001 is to produce objective evidence. And to that extent, we're trying to evaluate electrochemical reliability. And electrochemical reliability can only sensibly be done by utilizing insulation resistance testing, because that will not need to differentiate between ionic and non-ionic contamination or issues that may arise. Once you've established a good material set data, then controlling the process is what the old Rose test was always intended to do, only a process control. But because that number is used by everybody as their pass-fail, it doesn't necessarily reflect accurately across every single producer. Trying, therefore, to establish process control needs a different approach to the testing, and what I've put in place through IEC is a new process ionic contamination test method that will be published early next year.
Okay, well that's an interesting approach, so we'll look forward to seeing that. Obviously you're referring to the old standard where I think it was 156 grams per square centimetre or something like that was the IPC number, which has been replaced. Mark, what do you think about what sort of data choices manufacturers should be considering?
Well, SIR testing, just as Graham was said, the key point to the whole thing is that we need to be able to collect objective evidence by doing the proper material characterizations on our processes and our material choices to ensure that we understand what level of cleanliness is underneath our component sets and on our assemblies per se. Mm-hmm. So that's the objective that's trying to be obtained now through the J Standard Cleanliness Section 8 guideline. So SIR, or surface insulation resistance testing, is the right method because, just as Graham said, it allows us to get an insulation resistance number, whether it's 1E8 or 1E9 or log 10, however you want to represent it. The point now is it now allows you to get a very good number and a resistance reading, right, of what is actually on your board and underneath your particular components. Right. And from that, both the end user and the manufacturer can make a decision: am I clean enough, right, or am I too dirty, right? It allows you to answer that question. Mm-hmm. Am I clean enough? Am I too dirty to be able to meet the end design objective for that particular piece of hardware? Right. And that's the objective that's being driven by the industry now. Mm-hmm. And the tool set to do that right now is SIR testing. Okay, interesting. Of course, one of the things with SIR is you need to try and get the results immediately. We want to try and get them straight away. Tell me, Mike, what processes are you trying to control on the line?
Well, if you look at the question itself, what I like to do is always focus back to the problem. And the problem is that today we're seeing higher density circuit assemblies, we're seeing smaller components, and we're seeing components that have a tighter distance between the signal pins or the conductors themselves. And so what does it really mean for an assembler, and how do they detect that? Part of what Mark and Graham mentioned is that if you do insulation resistance, you now get the ability to really design test boards that are consistent with somebody's production hardware, with the challenging components that are on their production hardware. And by doing that, you can make assessments as to the material choices, whether they be your soldering materials, whether they be cleaning processes, and if you do clean them, have you cleaned them adequately enough? And so by doing that, you can start to really make data-driven decisions based off what's on the board itself from a reliability standpoint. So it's kind of changing the approach that people have done in the past. Surface insulation resistance testing has been around for a long period of time.
Right.
Graham, and what he does, he knows that testing because he's been in that business for a long period of time. But it's really taken a different mindset. Can we take the power of the instrumentation and make it a process control tool that can look at lot-to-lot variations, and can we look at it differently than the way it's been looked at in the past? Once you've done your qualification and validation, if you have residue underneath these components, you can detect it quickly. Mm-hmm. And you can use a tool like this to really bring a lot of information and data-driven decisions to the manufacturing environment.
So do you think it's important to be able to do lot-to-lot comparisons and that sort of thing?
Yeah, the situation is that in order to obtain objective evidence, the customer or the user is going to have to characterize a pretty wide range of process conditions and process materials, trying to find out if they are synergistically compatible with one another is the first step. Now, there is a new standard shortly to be published, which is a revision to an existing document that is process control using SIR techniques.
Is this an IPC standard?
I'm sorry?
Is it an IPC standard?
No, this is an IEC document. It's been around since 2007, but it hasn't been as widely embraced because companies are reluctant to go down this route because it is a new test program. It's time consuming, it's not cheap. It is vitally important though, and trying to get the material set brought together is the tough part. So there are two steps to doing this work. First is to use a simplified package, a simplified board design that allows you to determine at least the principal parameters before you then go for a complete comprehensive use using the IPC B52 test vehicle, which we designed and developed to try and help users examine how they all play together. Mm-hmm. Only when you've got that completed can you move forward. But keep this in mind. We have got industry challenges that go from medical space applications where we are working at ultra-low voltage, ultra-low current, to the other extreme where it is in electrification of vehicles, and we're up at 1250, and I know we've got customers in China that are actually testing at 2500 volts for 2,500 hours.
Wow.
And they're trying to find out what are the breakpoints in their process and understand what they need to put in place to fix it. Now that is insulation resistance testing, but it's not process, it's not on the surface, it's below the surface. The circuit boards are the key issue that people are having to address, and that's the test we call CAF. So these all kind of go together, but the parameters produce some challenges for the supply chain to try and provide the objective evidence that covers their particular requirement at one end of the extreme to the other with others.
So you've got people using boards with 2,500 volts in automotive?
Yes.
Wow.
We've even got some that are wanting to test at between 3,000 and 5,000 volts. Now, we all know when you're testing in a damp heat environment, testing at something greater than 300 volts is a health and safety challenge.
Okay. You got any comment on that, Mark?
I agree with Graham. We're starting to see limits on both ends. Mm-hmm. So the electric vehicle is pushing us to higher voltages, which are driving a new sets of concerns, because now things operate from a physics standpoint slightly different when we start achieving volts that high. And the dielectric gap and the spacing becomes quite a challenge. Not only is it a safety challenge on being able to test it, but all of the test gear and everything has to be viewed on how to be able to achieve testing with these very high voltages.
Right.
And that's why the electric vehicle is pushing that forefront. But a bulk of the industry is on the opposite end, right? So there's really going to be SIR testing with a split, right? You're going to have a bulk of the world that's worried about low voltage and low current, and you're going to have the other side of the spectrum where it's going to be power and high voltage. And those are going to be, we're still going to be talking about SIR, but we're going to be talking about SIR in two different fashions, and the testing is going to look totally different.
Right.
Not that the results of what we're trying to achieve is going to be different, but remember, the method of being able to get the data that's beneficial is going to look and be different.
Right. So basically you're going to have the low voltage stuff obviously on the entertainment systems and the instrumentation in the car, but the powertrain is going to be in the high voltage.
That's correct.
Level. So, the car's not getting any bigger, but the amount of electronics going into it is increasing. So how big a problem is this, Mike?
Well, it can be a big problem as we look at why there has been a change in these standards. Is that, again, it gets back to the insulation aspect. When you decrease that insulation space, and insulation can mean a number of different things. Mm-hmm. It can mean the cleanliness. It can mean the distance between the conductive paths. It can mean many different factors, but as you look at the insulation piece, a lot of these residues are out of sight. You can't see them. And in some respect, it's hard to inspect for them. If you're doing the old method like a bulk extraction, you're not going to detect residues where the source of the problem truly are. Right. So what we've tried to do is we've tried to look at that phase of the problem and say, if we can detect them, how can we bring that information back in a rapid way? And I was just looking at your publication that you have here at the show, Trevor, and you talk about smart digitization, and smart analytics. And we think about machine learning and the smart factory. That's where we're trying to go with this whole test technique, right. Is we're trying to create an avenue where we can get to the data, we can understand it quickly, and we can start to monitor it as the test is taking place. Right. So that we can look at it differently and we can start to slice and dice the data in a different fashion than what it's been done in the past. And if we can do that, we can start to learn from the data, and we can start to see what the data really means in different situations. And so it's trying to take a creative, different approach toward the problem to say, can we get better at the problem to try to understand it and try to get true meaning from it.
Right. Okay. Well, it's certainly true. In all other parts of the process that the industry is driving for, everything's getting faster, but they're wanting more traceability, they're wanting full data analytics with that, so that they can basically correct issues in real time, and rather than waiting till a week later and how much scrap did we make?
That's a big issue that people have got to get their heads around, in the sense that in order to run insulation resistance testing, and I'm not talking about surface, I'm not talking about CAF, I'm just talking about insulation resistance testing.
Right.
You have got to carry this out in a damp heat environment.
Mm-hmm.
Without the presence of moisture, a circuit that's got ionic matter under bias, there shouldn't necessarily be a problem.
Right.
It's only when you've got all three conditions together that problems occur. When you initiate a test to evaluate this performance, the chamber has to be set at one of two different test conditions. Either 85-85, which is if you are running a cleaning process, 40-90 if you're running a no-clean process.
Mm-hmm.
Why is there a difference? And it is from experience, and keeping in mind that the initial research for all of this kicked off big time in or around 1987. And I've been intimately involved in all of that research ever since. What we've established is that, unusually, and it's almost in the face of Ohm's law, the lower the voltage, the greater is the potential for electrochemical failure.
Right.
And that surprised the heck out of everybody.
Mm-hmm.
Why that should be, nobody fully understands, but from my own viewpoint, I believe that it's to do with the amount of surface energy that is being presented to that circuit. And if it's not high enough, and we're measuring current, we're not measuring voltage, to that extent, how much current can escape discovery of electrochemical failure? If the voltage is too high, it may blow it off the surface before you can even see it.
So let me see if I understand you here. Are you saying that if the voltage is lower, then the current looks for a way to escape from the circuit in some sort of dendritic growth? Is that what you're getting at?
That is essentially correct.
Yeah.
The amount of electrical current that we're measuring can be, and is typically around the picoamp level.
Mm-hmm.
The instruments have to be very carefully calibrated and set up to be able to detect these very small currents, picoamp levels, and we're even being pushed by the users to go down to femtoamp levels. And I keep bringing everybody back and saying, hang on, we're trying to predict failure, we're not trying to prove how high a number we can get.
Right.
Because it's getting the performance characteristics of the end product. So when you now talk to the people in the world of medical electronics, much less wearable technology, there's a completely new requirement, and trying to get them to understand, using a magic number that has been for 25 years or more, to my knowledge, of 1.56 micrograms per centimeter squared of sodium chloride equivalents is nuts.
Right.
I've got customers and users who are actually delivering product with guarantees on warranty for ultra-high reliability and safety-critical applications where their pass-fail number is at 2, 2.5,
Right.
3, why 1.56? And then there's others at the other end of the spectrum, their pass-fail is down at 0.1 or even lower.
Depends on the product, the design of the board, and a whole range of other things.
Correct.
Right. Anyway, I want to just move on before we wrap up this discussion onto the more general area of cleanliness testing. I mean, there's still 80% of the people that are coating boards are not cleaning. So where does SIR fit into that?
Well, it's a very important part of it. So if you're going to coat your boards, you need to understand what you're going to entrap underneath it. So SIR testing allows you to get a surface insulation resistance number of what is happening underneath those components before you seal it up.
Yeah.
A lot of people do not fully understand that an FR4 structure actually is an organic structure that breathes and absorbs moisture as well, right? So we're encapsulating the surface, but we still have the ability to bring water molecules up to the residue that's trapped underneath.
Right.
So whether you're using a no clean or a an RMA flux system, it really doesn't matter. What's important is that we get objective evidence to know what our surface insulation resistance value is before we conformally coat it or seal it.
Right.
Whether we're underfilling, I have a lot of clients in both the military and the medical field that underfill their components to get added dielectric insulation, right, value to it. But what they fail to realize is that if there's 1 to 2 or 3 mils worth of residue that's not fully catalyzed, right, catalyzed over or flashed over, however you want to terminate it, and you underfill it, you're trapping a layer of either ionic or non-ionic, and it doesn't matter, right?
Right.
It still has the ability to affect your resistance, and it's not always, a hard dendrite. It can just be that we have a residue that is allowing us to have leakage currents, right,
Yep.
across it. So the important thing here is that SIR testing allows you to get an understanding of how clean you are or how dirty you are, and then you and your customer make a decision, is this where you want to be? Are you happy with that? The sealing it up is an ideal way. I mean, there's lots of conformal coatings out there. They're trying to prevent water ingression.
Yep.
But remember, everything to some certain extent has some moisture absorption rate. It can be low, but it's not zero. The board, right, is another way of absorbing from that.
it.
So the key thing here is that the industry needs to be educated, and we need to grow and we need to educate. But the tool set that's needed is SIR for people to make very good decisions on their material characterizations, their material processes. So all things, it is not a single variable event that causes you failure, right? So it's your material choices, which can be your fluxes, it can be your conformal coatings, it can be any of your other add-on peripheral things that you have to do to be able to build your assembly. But the one key element that was needed is the element that is continuing to grow, is that SIR has been with us, and we're becoming to use it greater and greater to drive us to a data set that allows us to make a better decision.
Right.
And we need to view it as a tool and as a guide, right, and as a way to judge, but not necessarily think it's a panacea that it's all inclusive, right? It's not the perfect answer, but it is a better answer to what we've had.
But I think the key thing that you highlighted there is it's just as important to use SIR testing for even in a no clean application as to whether or whether you're cleaning. So it's important that you use it in a no clean as well. Which I'll give the last word to you, Mike, because there are problems with QFNs where it's difficult to validate because you can't penetrate that encapsulation.
Yeah, QFN is a lot of research has been done on it. One of the challenges is that you've got the large thermal lug underneath the center. You have a common pitch of like 0.5 millimeters that could even be reduced. So you see a component that when you place it onto the board, you have an average of between 1 and 2 mil standoff gap. What we found is that as that standoff gap drops, if you don't have the channels for the flux to properly outgas, you can leave activators that don't decompose and part of the solvency portion of that flux. That in itself, as that device is deployed and comes up to temperature, could be the mobilized area that you could see migration and get leakage currents. That's one area of possibility. But one of the areas that SIR can also be used is it can be used in PCB board design. We've done work on QFN areas where we say, how can we get a better outgassing channel and how can we prove it? Mm-hmm. So as you start to look at the IPC 7093 document that's going to be released at Apex this year, they talk a lot about encroached vias and solder mass defined areas where those vias are. We've done some research in that area where we look at an open copper versus patterning different via structures and do SIR, and you can see a difference in the design of the printed circuit board as far as those outgassing channels. And if you were going to run a no-clean process, you can utilize that information to see where do I get a more reliable part if I'm going to place it. So it's a very powerful tool in not only looking at material characterization, but going upstream and looking at the design attributes as well.
So you think designers should really start looking at SIR to come up with a design for cleaning strategy?
Well, I think, go ahead.
Forgive me. I was just going to say, one of the big issues that arose fairly recently, I mean it's been around for decades, is subsurface insulation resistance breakdown in the form of CAF. And one of the things that concerns people is, well, what is the actual failure mechanism? Nobody's entirely sure as yet. We've got problems of corrosion, we've got problems of creep, we've got problems from a multiple of different sources. And when you have a circuit board to be evaluated, what is the nature of the fabrication process? And through the research that is still ongoing, particularly with the National Physical Laboratory in the UK, where I have an almost symbiotic relationship, we've got a situation where the CAF formation is often driven from incorrect weave of the glass fibers in the process. And one of the points that was made by some of the other study members was, well, how important is the weave and the filling of that weave when we're trying to evaluate the performance for these new technology drives?
Right.
And what we discovered, or I made the comment, well, are you still using E-grade glass to spin the fiber? Yes. And I said, well, E-grade glass is really mostly these days recycled material. And I would recommend against using that. You could do with using a better grade of glass in the fabrication of the board. In a previous life, I made or was involved in glass making programs. So it's something that I knew about from 40 odd years ago.
Right.
So I know that certain manufacturers of laminates are now embracing a much more careful consideration on the density of the fiber weave, the location of the vias through that weave, because when you're drilling, as Mike was saying, finding these evidences from vias,
right,
you are not drilling by cutting, you're drilling by smashing. And of course that stresses the laminate and thereby allowing a situation where low surface energy materials, whatever they may be, especially flux residues, if they're not properly reacted, you've got an amount of liquid on the surface that requires a higher preheat in your soldering process, and therefore there is absorption of these processed materials into the laminate,
right,
from which they can't easily escape. But when you expose them to a deionized solution, which hates being in that state, it wants ions. So it goes looking for it. So many of the tests that we've been reviewing over the history of this is actually leachates. It's material being dragged out by the use of alcohols and water to try to carry out what everybody unfortunately refers to as a cleanliness test. That's why I have a real thing about that. Right. Try and stop thinking of it that way.
It's certainly it's a fascinating area and an area I hadn't considered before. But between what you've been saying and what Mark was saying about bringing the the absorption up from the board, it really opens up a whole new area of research that needs to be done here. But anyway, gentlemen, unfortunately we've run out of time, but I want to thank you very much for your very in-depth discourse today, and what do you call it, in such a friendly manner as well. Graham Naisbitt from Gen 3 Systems, Mark McMeen from Magnalytix, and of course Mike Bixenman from KYZEN Corporation. And thank you for joining us today.